Hi there, my name is Stephen Fields, and this is the final presentation for my independent study on academic paper recommendations for my master's in data science. So for this presentation, here's a quick overview and what to expect for what I'm going to be going over. Starting off with what the project is, why I chose it, how do you compare text, summarization of the technology I used, a quick demo of the application, walkthrough of the code, and ending off with a results and potential improvements slide. So what is this project? Well, the aim of this project was to create a visualization that will help users identify relevant research to fill in any potential knowledge gaps they might have before reading the paper they initially intended to look at. While all academic papers include a reference section, reading titles and authors alone often isn't enough to get a good idea of what to look at first. So why this project? This project idea came mainly from my own experience conducting research for my various classes. Data science is a rapidly evolving field, and it can be difficult trying to read a state-of-the-art piece of research without having the background knowledge on some of the research that came before it. I found myself in this position several times and always wanted an easy way to figure out where to start, but could find little to nothing online for it. As my master's was wrapping up, and with the experience I gained through previous coursework, I thought it would be a fun and exciting challenge to tackle for my capstone, as well as an excellent opportunity to work with some new technologies and apply them. But how do you compare text? Well, historically, this has been a difficult problem in computer science. But in 2017, a paper titled "Attention is All You Need" came out, and since then we've seen an explosion in capability from large language models. Soon after the release of Attention is All You Need, Google created a model called BERT, or Bidirectional Encoder Representations from Transformers. This BERT model is capable of a multitude of NLP tasks, including sentiment analysis, text prediction, summarization, and of course for this project, text similarities. For a high-level summary of how we compare the text, we run it through a BERT model or transformer model. We retrieve the last layer of tensors, which is a two-dimensional list of numbers between 1 and 0. After that, we mean pool or average the tensors into a one-dimensional list of numbers called a vector. We repeat this for another piece of text, and then we compare the vectors using cosine similarity. In other words, we normalize or scale the vectors and then perform a matrix multiplication on them. This results in a single score between 0 and 1. For example, 0.88, which would show a 88% similarity in the papers. To tackle this specific project, I used a variety of different technologies. Starting off with the dataset, I utilized the OpenAlex dataset, which is a publicly available dataset comprised of academic journals and their various data, such as title, abstract, authors, and more. I then feed the data I receive into a version of BERT known as Open Academic Graph BERT. This model is an augmented BERT model that not only compares the abstract text, but also the title, authors, concepts, affiliations, and publication venue. From there, I scale the vectors retrieved from the model and store them in a vector database called Milvus. Milvus has a multitude of capabilities for quickly performing similarity searches that I originally experimented with, but it currently just acts as storage for the embeddings, or vectors. To retrieve data from OpenAlex and create the embeddings in real time, as well as the similarities, I built an API using Python's Fast API. The reason I chose this was due to it being a lightweight and fast framework for quickly building APIs. And it's called Fast API, so it's got to be fast, right? Finally, for the front end and visualization aspect, I utilized a JavaScript library that is actively under development known as Helios Web. Helios Web is a library focused on visualizing dynamic networks in real time and is being developed by Filipi, Silva, one of my advisors for this project. Now for a quick demo let's open up a local setup of this project or application. So first off, you'll see that it's loading. You'll see a loading screen where it's currently fetching papers. Once it's done fetching the data for all of the papers, it will create embeddings. Usually this process would take much more time, but I've ran this specific paper before. Once the embeddings are done, it computes similarities, and then we see this visualization right here. So for this visualization, this is on the attention is all you need paper, as you can see in the upper left. Starting off here, the node sizes are determined based on the similarity. So the root paper, or attention is all you need for this instance, will always be the largest node on the graph. From there, the similarity score is used to calculate how much smaller the next node will be. So if a paper is 99% similar to attention is all you need, it will be 99% the size. Whereas if it's 1% or less, it'll be much, much smaller. Once the visualization is up, you can hover over any of the nodes and see the title of the paper, as well as the similarity scores between its parent and root. So the parent is the paper that references the paper you're hovering, and the root will always be the original attention is all you need paper, or whatever was searched. As you navigate this, you are not stuck to this single focus point of the original root node. If you instead see a paper you are interested in, such as this Roberta paper, if you click on the node, it will let you zoom in and focus on it so that you can better see what papers it uses as references. And then from here, you can also click on edges between two different nodes and focus on them together. Anytime you find a piece of research that you would like to actually view, if you double click the node, it will bring you up to its, on occasion, it will bring you directly to the paper. So for attention is all you need, if I double click this one, it brings me directly to the paper. Otherwise, it will take you to a website where you can then find the paper and read it there. There are situations where you require access to the specific website. There's no good way for me to counteract that, but it is very rare. Most of these are all open to the public. Next, you can search for new papers. I would like to demonstrate how slow it is. So how slow it is for new papers that it hasn't seen before. I guess ICE won't show up internal combustion engines. So you can search for a new title here, and as you saw, it auto-completes. This depth slider right here is the number of paper references you want to find in a sense. So 1 would just be getting attention is all you need, so it's disabled by default. 2 is attention is all you need, and it's direct references. And then 3 is the references of those references, and then 4 is another layer, and 5 is another layer. Quick warning on that. For attention is all you need specifically, depth of 3 is 400 papers, depth of 5 is 8,000, and depth of 4 is 8,000, and depth of 5 is like 140,000, I think. So the number of data points grows exponentially, and so does the time that it takes to compute that. So if we search up the internal combustion engine fundamentals, we have a color scheme here. This one is by default, it's called cool. I just thought it looked the best, but it can be changed to any of these different ones. So if we select one and start running the search again, it again fetches all of the papers. It will then compute similarities, which will take more time now because Again, it hasn't seen these papers before. Luckily, there was only 100 papers, so it didn't take too much time. But like I said before, it can quickly grow out of control and take hours to compute. So here we have the new paper on the fundamentals of internal combustion engines. And like I said, sometimes it requires access. So let's ignore that one and try one of the references. Here we have a very old paper that has been photo scanned in. Yeah, that happens too. It all depends on when the paper was made. For newer papers, usually the references are also fairly new, so you'll get directly like a PDF of just the Word document, but things happen on occasion. Next, we will go through a brief code walkthrough. I'm going to skim over a lot of it because I'm not sure how much of the audience will actually be interested in this portion. But this is where I define 4 total endpoints for the API. So there is getting a specific paper. This is used to get the root paper, or the one that you search for in the beginning. This endpoint gets the root papers, or it gets references for any paper that you send it. So if you send it attention is all you need, it will get all of its references. If you send one of those references, it gets that paper's references and just returns it in a list. At this endpoint, we calculate the embeddings. And then finally, once this one has been completed through all the rounds, we calculate similarities at this endpoint. Going deeper into that, let's see. So for creating the embeddings, we see if the papers are already in the Milvus instance. If they are not, then for each paper, we create the inputs for the model, and then we do a forward pass in the BERT model and retrieve the pooled output. We then normalize that output and save it to Milvus. When we go to compute similarities, we take a target and source list, and then for each paper in the sources, we query the vectors we recently got, or we query the vectors from the database, and then we do a matrix multiplication here that returns us that similarity score. So here we specifically return a list of similarity scores between a target and source list. We then iterate over it because we do the root target. We have the root and the parent, and we iterate over a list of sources. For the autocomplete JS on the front end, this is all of the front end work for that little modal in the top left of the screen. This right here will toggle between the loading screen and the visualization. These are just various things to get and fetch papers. And here is adding the papers for the autocomplete section. We just listen for whenever anything is input into the search bar, and then we display the papers. For the actual visualization portion, this has a lot more because this is showing status updates as part of the loading screen. It is fetching all the papers, the references. Here we create the embeddings and similarities. This is just a wrapper for the others so that we get all of the references to the certain depth that the user inputs. We get all of the similarities for all of those papers. This is the tooltip code. Basically just takes the color of the node, darkens it, and displays it. This is the part where we change all of the color schemes. It's just a list of different D3 color schemes. And here's the actual point where the visualization is called initially and created. We call all of those previous functions, and then we create a Helios instance. And then we set up what edges can be clicked on. This right here just makes it so that you can click on all of them. We set the size of the nodes, the background color. Here is where the majority of the actual size of the node is made or calculated. So we take any source edges and they're the source like node size, and then we multiply the average of all of the similarity scores to that in order to get the new size. This sets the color based on the color we had, based on the color scheme and the size of the node. The outline color, we just make it a little bit darker so it's easier to see on the visualization. This is that zoom in effect when you first see the visualization pop up. This shows the tooltip. This right here will focus on the node that you clicked. This is to open it in another screen. And then here it also focuses on the edge. And yeah, that's about it. We listen for when the submit button is clicked to switch the display off. Well, toggle the display, which means we switch it back to the loading screen and then call create visualization. If we go back up here, once Helios is, right before Helios is ready, we toggle it back so that it's showing the visualization instead of the loading screen. And this right here just starts it up. So on startup, when you first go to the website, it automatically begins to load that attention is all you need paper. That covers it for the code walkthrough portion, at least what I wanted to get through. There is more there, and there's other notebooks within the repository that will show you some of the experiments I did early on. I originally experimented with another version of BERT other than Open Academic Graph BERT. But finally, as for the results and potential improvements, it does visualize the most similar papers to one and provides quick access to them by opening up the PDF. It's set out to do exactly what I was hoping to get out of this project. I'm very happy with it. But that being said, there are some improvements I can see being made to it. Like currently, I get all of the references for every, or I get all of the references to a certain depth. To speed it up and get more relevant information, I could only get references for the most similar papers. So like from attention is all you need, I get all of the papers, calculate the similarities, and then take the top 5 most similar papers and then get their references as well, and then do that 3 or 4 times, and it'll give like a better idea of, well, I wouldn't say better, but it'll give more of a path you can take to learn your way up to the initial paper. And it would also save dramatically on resources. I wouldn't, instead of the 140,000 papers for depth 5, it might be 2,000. That's one dramatic speed up that I could do. Another improvement would be parallelizing the vector creation. So right now I iterate. So for each paper in the list that it's given, it creates embeddings one at a time. I could parallelize that so that it creates embeddings for 5 to 10 papers at a time. I do have concerns with that approach. The embedding creation was fast on my machine, but I have a NVIDIA graphics card, which helps with the AI acceleration. If you try that on a CPU, for instance, or just like any old laptop without a graphics card, it will take much longer. like an order of magnitude longer. There's nothing I can really do about that. That's just, part of the problem. Like anything with AI requires GPU acceleration to be performant at all. But yeah, that concludes this presentation. I'm open to any questions and suggestions, and thank you guys for checking this out.